All right. Good morning, everyone. Welcome to Physical Geology 1403. Naomi, awesome. Would you mind grabbing the door for me? We need to keep that closed at all times as long as I have students in high school in my classroom. All right. Thank you very much. Hello, everyone. My name is Josh Hart. You can call me Josh. You can call me Mr. Hart. You can call me Professor. You can call me whatever you like. I'm going to be teaching you geology for the next 8 weeks. Hooray! And then maybe for the next 8 weeks after that, if you're taking 1404 from me as well, depending on your program, your area of study, they might have given you both sections with me. It's not always the case, but I enjoy it when it is because we get to explore lots of really cool, interesting stuff together. Let me tell you a little bit about myself, and then we'll go around the room and talk a little bit about yourselves, all right? This is actually a very old picture. This is a 2-year-old picture that I just have not updated yet. I finally updated all the family pictures in my office yesterday after 2 years of keeping old photos. So I will get to this probably later today or later this week. But anyways, this is my family. My name is Josh Hart. I have a wife. I have 3 kids. My oldest son is 7. My daughter is a middle child. She's 5. My youngest is 3. You might actually see them every now and then. They like to stop by and surprise me. My wife occasionally will come and sit in my class. Every term we have a silly geology movie night where I offer extra credit for y'all to come and we watch a movie that we've all voted on that has some ridiculous science in it, and we absolutely eviscerate it together, and I give you some extra credit for that. And my kids usually come and like watching that with us. So you might see them every now and then. But a little bit about me. I have an associate's degree from Sinclair Community College in Dayton, Ohio. So I've done the junior college thing too. I know what it's like. I have a bachelor's degree from Brigham Young University in Idaho. That's in geology. I have a master's degree in geology from the University of Louisiana at Lafayette. And I'm just over halfway through my PhD from the University of North Dakota in lunar policy. So my research is developing the rules and laws people will live by when they go to the moon and start developing it for resources and how those resources are shared. I'm in my last class right now for that. And then after that, it's just dissertation and publishing. So I can't quite see the light at the end of the tunnel, but I know that it's up there somewhere ahead of me. Right? The darkness is starting to lighten up a little bit for me there. I have tons of different types of work experience in geology. Most of my research up to this point has been in paleontology, so the study of ancient life. We are going to talk about that a little bit in our class here. We are talking about that a lot more in 1404. So if you like the idea of learning about the history of life on Earth, please take 1404 from me in the next 8 weeks as well. I have experience in mining. I worked at a gold mine in Nevada for a while. I have experience in the oil industry. I've worked in North Dakota and Montana, as well as doing some consulting work around here. I've worked as a museum curator. I've worked as a tour guide. I've worked as a paleontologist. I've done a lot of different types of work in my career. I've taught here at Odessa College for the last 5 years. It is crazy to me that it's been that long. This is actually the longest I've ever been in any one location. Okay, so my dad was in the Navy when I was a kid, and then I became a geologist, and we travel a lot. And so 5 years here is the longest I've ever been anywhere. Prior to that was 4 years in Japan, and then otherwise it was 1 or 2 years in other places. So it's been a bit of a learning curve to stay still. You'd be surprised after a lifestyle like that how hard it is to just stay still. But somehow I managed it. Don't know how much longer I'll be here. We'll see. We'll see where things go. I don't know what my career will do after I finish my PhD, but here I am for now. Let's see. Any questions about me or anything before we move on to talking about you? Anything? Any questions about my career or anything that I've done? No?
Yeah, how of all places did you end up in Odessa, Texas?
That's a great question. How of all... Yeah. So just so I can clarify for the people listening online, the question was, how of all the places did I end up here? Well, all the places is right. I've lived in a ton of different places. I've been to every state in the US. I've been to half the provinces and territories of Canada. Lived in Japan, been to Germany, Austria, Switzerland, France, Scotland, Ireland, England, Iceland. I've been all over the place. How did I end up here? I was working on the Keystone Pipeline in Montana. Do you ever hear of the Keystone Pipeline? The Keystone Pipeline was that really big pipeline project that everyone in the Republican Party that's been in the White House for the last 20-something years has been pushing really hard for, and then every time a Democrat goes in, they shut it back down, and then a Republican turns it back on, and a Democrat shuts it back down. It's like a tug of war. It gets in the news every time there's a new president because one of the first things that they do is either turn construction back on or turn it back off, right? So back during the first Trump administration, I was working on the Keystone Pipeline as a paleontologist. Because they were digging through layers of rock that contained dinosaur bones. They needed a paleontologist on hand to remove the dinosaur bones if they were dug up, because it's against federal law to destroy those if you dig them up. They are protected under federal law. So I would be there on hand so that I could remove the dinosaur bones quickly and they could continue construction of the pipeline. Well, August 2020 starts rolling around and I see the way that the election is starting to veer. And I'm like, I probably shouldn't be working on a pipeline come November. And so I started looking for another job. And on top of that, I needed something that would let me be with my family more anyway. Doing 15 hours a day on the pipeline was not super fun. Fantastic paycheck, but not great when you have a family. So there was an opening for a geology professor here. And so I started teaching for them online that August. And then it went so well that I think it was November 1st, actually, I signed a full-time contract, quit the pipeline, and moved down here. And then later on that month, 11,000 people got laid off on the pipeline because President Biden shut it down his first day in office. So that was the reason, kind of twofold. There wasn't much career prospect where I was at the time, and I needed a job that would give me more time with my family. So that's why I ended up here. Now, why have I stayed? I needed to practice commitment. After spending so long bouncing around the world, I needed to spend some time places. I committed to spend 5 years here, and now those 5 years are up, but I'm in the middle of my PhD, and picking up and moving in the middle of a PhD program is not a good idea. I really don't want to derail myself, so I'm going to be here at least until I finish it. Yeah, great question. Thank you for asking. One other thing about me, I enjoy acting, specifically theater acting, right over there at the Globe Theater. I've been in several plays over there. And there's also someone in this class, Emma right here, who acts over there with me every now and then. She's a fantastic actress, and I am tickled pink that she's in my class now. But we're going to go ahead and introduce ourselves a little bit here. Let's go ahead and start with Emma, actually. I want to know your name, where you're from, what your major is, and what you want to do with your life.
My name's Emma. I'm from Odessa. My major for my associates is general studies, but my bachelor's degree when I go to college officially will be marine biology, and I want to be a marine biologist.
And tell me, have you gotten accepted at a college somewhere already?
Yes.
Where are you going?
Texas A&M University in Corpus Christi.
Woohoo! She's going to Texas A&M Corpus Christi.
Oh, okay.
Yeah, we're all really excited for her. I'm really excited for you. Okay, so that's Emma. Thank you, Emma.
My name is Jared. I'm from here. I'm from Odessa, Texas. Mine is also general studies.
Okay.
And right now, I don't know yet, but I want to do something with aerospace engineering.
Aerospace engineering. I love it. So construction? Okay. Are you thinking like ships or structures?
Like shit.
Ships? Okay. All right. We might work together at some point then. If I'm working on lunar policy for how people get to behave and share on the moon, and you're building ships to get there, we might cross paths in the future.
My name's Aiden, but I go by Cole.
Aiden, but you go by Cole.
Yeah, Cole.
I will try to remember that. You wrote Aiden on the card, so I'm probably going to call you Aiden.
Oh, you said first name.
Yeah, sorry.
Born and raised here. My major is in general studies, and then when I grew up, I want to continue doing my lawn business and maybe open a gym one day.
Open a gym. Nice. Love that. Cool.
My name is Sergio. Oh yeah, my major is general studies as well.
Okay.
But something I've been wanting to do is petroleum engineering because we live out here in the west. So,
Yeah.
Pretty local.
It's a great place to do it.
Um,
Yeah, your name, where you're from, your major, and what you want to do with your future. And you kind of already said that. Your major is petroleum engineering, and you want to work in the oil field out here. Any particular aspect of the oil field that you want to work in?
I haven't thought about that yet, honestly.
No?
Yeah.
Okay. All right, cool. I always appreciate it when petroleum engineers come through my class and actually try and understand the science behind what everyone is doing out here, instead of just being content with, I build stuff, right? There's a lot more behind it. How do we find the oil? What is the oil? How does it form? All of that, the things you're going to learn in this class. I like it when petroleum engineers care enough to try. So thanks for being here. All right, Leroy, is that? Awesome, go for it.
Yeah, I'm Leroy. I'm from Odessa, Texas. Right now I'm in general studies, and I either want to go into accounting and then become a CPA,
Okay.
or go into petroleum engineering.
You know, right off the bat, CPA and petroleum engineering sound very different, but there are so many numbers that go on in the petroleum industry that having experience in both might actually be beneficial. So, cool. Good for you. Leroy, all right, yeah.
My name is Naomi. I'm from Mexico. My major is business administration, but I want to be an accountant. And I'm planning to go to
UTPB?
yes, exactly.
Great. Do you graduate this May? Oh, and then you're transferring straight over there? Good for you. Good for you. Yeah, for, let's see, how many of y'all are graduating in May? Everyone? Hey, yo, look at this. Just so you know, I always sit on the front row at graduation so I can high-five anyone I know on their way past me to get their diplomas. They've told me so many times, stop that, it's not professional. I'm like, you got it, and then I'm just going to keep doing it.
Just a sign of a good teacher.
I appreciate that. Thank you. I hope that I'm a good teacher. We'll find out over the next 8 weeks. Okay, but yeah, no, I mean, the connections we make and the fact that you actually come and listen and you pay attention and you actually do the work means a lot to me. So I want to be there for you guys on your big day. Okay, fantastic. And you said accountant, and you're transferring to UTPP to get a bachelor's in that. Very cool. Very cool. Let's go over there.
My name is Ivani. I'm from Midland, Texas, but I was raised here in Odessa. My major is general studies, and then after this year, hopefully I plan to move to San Antonio and pursue my degree in ASL.
ASL. Very cool. Why ASL? What took you to that?
I don't know, just something that I've always been into. I was also a teacher for like 3 years.
Great.
Since I got out of high school.
Mm-hmm.
So it's just something.
Were you teaching at like a local middle school or something?
No, like elementary.
An elementary school.
I live in.
Okay, right, yeah. Cool. Awesome. Good for you. My wife knows ASL, and she's taught me things every now and then. Like, and I don't remember most of it, but I like it. It's cool. Great, good to go. Yeah.
I'm Lexi. I'm from San Angelo, but I moved here like a year and a half ago.
Okay.
My major is early childhood education. Probably gonna end up switching to math,
Okay.
just so I can teach high school.
Okay. Yeah, yeah.
Yeah, because I'm not gonna be stuck with the gremlins.
The gremlins.
They are that bad. I was teaching in high school.
I went into third grade though.
That'd be the lowest I'd go.
So we'll do these things here called preview days. You guys know what those are? No? Okay, we used to call them OC invasions a couple of years ago. Okay, so you've heard of that. Okay, so preview day is we do this once or twice a term where every faculty member at OC will go to an elementary or a middle school, and every department will give some kind of presentation. So like I'll take my snakes and my turtles and some rocks and fossils and stuff, and I'll give a little presentation about my stuff. Biology department will do their thing, math will do their thing. And we go and we basically take over the teaching of these students for a day, right? And I've had classes that were gremlins, and I've had classes that were angels. So I think it really just depends on how the school conducts themselves, what their policies are, specifically for where it comes to managing the kids and how they act out and stuff like that. I've seen a real big difference between the schools here in
Well, I
Odessa.
was a student teacher in high school in San Angelo,
Okay.
so those kids might be different.
Yeah.
You know,
I mean,
they're not constantly inhaling the fumes here.
right. Yeah. Well, we do have some fumes that every now and then. The high schoolers here are just the worst. I can't stand them. You know, they just have.
Yeah, my high school's rivals with
I'm just kidding, guys. I'm just kidding.
Or these high schools are my high school's rivals.
Oh, okay. Got it.
I already don't like them.
The 5 of you are high school, right? Is it OCA? Okay, OCA. Great. This is something that I mentioned earlier, but now that I'm actually recording for the benefit of everyone to hear this, brand new policy is no high school student is allowed to leave my classroom early without very specific reason. I can't dismiss you early. I mean, I'm going to flub it every now and then. If I let you out 5 or 10 minutes early, please don't tell anyone, right? But I can't let you out 30 minutes early if you finish your lab early or anything like that. Can't do that sort of thing anymore. Y'all that are over the age of 18 and graduated high school, of course, that's your prerogative. You're paying for this class. You can leave whenever you want, really, right? High school students, unfortunately, have to be held to a different standard at this point. Okay. Great, we got to everyone. For my online students, by the way, you are watching this using a program called GoReact. Please feel free in the text section on the right of the screen to introduce yourself. I'll go in there and give, answer some questions. I'll go in there and learn a little bit more about you. You can comment, you can talk to each other. The thing I love about GoReact is that you can interact with each other asynchronously. So if someone else has gone in and left a comment, you can come in when you're watching it, and right there, time-stamped at that moment in the lecture, you can see someone else's comment and comment on that. And we can keep a conversation go asynchronously over the course of the week, even though we don't meet together, okay? All right, so a little bit of information about this class. This is my email address. Now, this is very important for in-person and online students. Do not attempt to contact me using the Blackboard message service. You know what I'm talking about? Where you go to the class page and it has messages right there. Don't use that. It's extremely inconsistent. I might get an alert that you sent me something on there a week after you sent it, which is probably too late to do whatever it is you were asking me in the first place. Okay? I don't get alerts from that. At least not consistently. The best way to get a hold of me is via my email right here. JHARDT, D is silent, silly Germans, right? It's the German name, Hart. Okay, jhart@odessa.edu. That is the best way to get a hold of me. My policy is I will always answer you within 24 hours during the work week and within 48 over the weekend or a holiday. Weekends and holidays, I'm sure you understand, my priority is my family. Okay? So, but during the work week, I will always respond to you within a day. For those of you that are here in person, you have the benefit of asking me questions in person. For those of you taking the class online, you can ask me questions on GoReact or over email, whatever you prefer. However, for my GoReact students, I do require you to participate in each one of the lectures. You need to ask questions. You need to respond to other people's questions. I need to see you do at least 5 or 6 different types of engagement in each lecture. That way I know you're actually participating. Whereas all of you here, I'll know if you're participating because you will be participating live with me. Please ask questions. I love questions. Questions are the heart of science. If you're not asking questions, we're doing science wrong. Okay? All right, so your syllabus is on Blackboard. I'm presuming y'all have had an opportunity to take a look at that, and if not, it's there for you. We just changed our syllabus format, brand new syllabus format. I don't even know if I did it right, okay? However it looks to you, if it looks like there's something missing, go ahead and let me know. There's a syllabus quiz that you need to do as a first day assignment. It's how I keep track of who was in attendance on the first day in person and online. If there is something missing from the syllabus that I asked about in the syllabus quiz, please let me know so I can fix the syllabus, okay? Because again, brand new system there. You don't need a textbook for this class. Yay! A few years back, I changed this class to online education That's OER, Online Educational Resources. That means that every piece of information you need for my class, I provide to you, or it is available to you online. I actually made a website for this class about 1.5 years ago, and the link to that website is in our Blackboard shell. It actually says class website. When you click on that, it'll take you to the website, and there you'll find the chapters in the online textbook. Yes?
I'm trying to look at the syllabus right now. It says you will be able to view this document, but it has not been completed.
You will be able to view it, but it has not been completed? Curious. All right, but it does let you see it. Is there a way to progress so that you can see it, though? It says you will be able to see it, but it is not completed. All right, well, that's bug number 1. Let me make note of that. Syllabus says not completed. All right, I'll take a look at that later. Thank you for checking that. Back to that class website. It has chapters from an online textbook, a free textbook that you can reference. It has some frequently asked questions. It has every lab assignment. It has everything on there that you'll need for the class. I want to caution you, though, the textbook is supplemental to me, not the other way around. I'm not going to be up here reading off of a textbook slide to you, right? I barely have any words at all on my slides. Everything that I teach you is up here. So don't expect that you can just not listen. This is for my online students especially. Don't expect that you can just not listen and still get by in my class, because there is no chapter in any textbook that will get you through the exams if you're not listening to what I teach you. Okay? I'm a very engaging instructor, not a passive one. All right? Looks like my camera froze up looking over there. There we go. Okay. Great. And if at any point you have questions, just stop me. This is what the general layout of our class is going to look like. I don't have any dates on here. The dates specific to your class section are in the syllabus. But here in week 1, we're going to go over the introduction. That's today. Then on Thursday, for those of you that take the Tuesday-Thursday class, we're going over matter and minerals, so on and so forth. Week 1, week 1, week 2, week 2, week 3, week 3. For my Monday, Wednesday class, it's going to look a little different, though the order is going to be the same. We did not have a Monday, Wednesday class, and next Monday is a holiday. So my Monday, Wednesday class gets a little screwed because they miss out on 2 days, which is unfortunate, but I don't make the schedule here. So it's going to be a little bit different than this, but the same format, okay? So that is the progression through which we will go in the class. Your labs follow a very similar progression. This week, you're getting your first lab. You're going to get that on Thursday. For my Monday, Wednesday class, they'll get it next week because it needs to be on their second lecture. Okay? But then it'll go in this order. There are 5 labs in this class. The first 4 are about sample identification. Okay? I'll talk more about that at the end of class time today. The 5th one is about how to read maps and interpret those. This is how the points are broken down in my class. Who here loves taking exams? Yeah, that tracks. I don't like them either.
They don't boost your score. They don't boost your score.
They can, depending on the grading distribution. That's true. Who likes timed exams even more? Yeah, they're the worst. I don't like those either. So, because I understand, being one of these people, that there are folks that don't like taking exams, only 50% of the credit in my class is in exams. The other 50% is in everything else. Labs, discussion boards, attendance, stuff like that. Extra credit. There's a little extra credit that can go on top of all this. Okay? I'll talk more about that in a minute. But that way, if you are just, just barely good enough or passable in an exam, even if you just got like a C- in an exam, but you really nail everything else, you're still going to do great in my class. Or if you're someone who's really good at studying for exams, but you're just not getting the labs, do the best you can on your labs and really focus on those exams, you'll still do great in my class. Okay? What will get you to fail in my class is if you don't put enough effort in either category. Okay? I've made passing my class very achievable, and getting an A in my class is absolutely a possibility if you put the right effort into it. Effort being the key there, okay? You need to make sure that you're putting enough time and effort into this class. It is an expectation, not of me, not of Odessa College, but of every learning institution anywhere, that for every hour you are in class, you are spending at least 2 hours on that subject outside of class. That is a universal expectation. We meet here in this classroom for almost 6 hours a week. Do the math. That means that the expectation is you're putting about 12 hours into this subject a week outside of class. Again, not my expectation, universities and colleges worldwide. Okay? We calculate everything out proportionally to that. We give you the amount of work that we think is justified based on that. Okay? Just bear that in mind. If at any point the workload feels overwhelming, it's based upon that calculation. Okay, so exams, 50% of your grade. There are 4 exams, including a lab exam, that you will be getting over the course of the term. Your discussions are going to take 20% of your grade. Now, for those of you that are here in person, there are going to be a series of discussion boards on Blackboard that you can participate in outside of class time. That's what I mean by discussions there. Okay. For my online students, the Go React lectures, where you can interact with each other and ask questions to each other and me and discuss things, those count for your discussion credit. Make sure you are participating in every Go React lecture there. Okay. Then the labs are 30% of your total grade. It's pretty significant because geology is a physical science. So hands-on labs necessary. For my online students, you have elected for one reason or another not to have a hands-on experience. But I have made over 40 hours of content on my YouTube channel of me doing every test possible on every sample in this classroom so that you can see the HD, the high definition video of me doing so. And that's what you're going to use to complete these labs. You're going to watch me doing the tests on your behalf and make your conclusions based off of what you see happening in those videos. That's the best that I've been able to come up with for an online format in this class. Okay. Now, everyone's question, what about that extra credit, right? Extra credit, it's great. I'm always going to encourage my students to put your primary effort into the actual work. Don't count on extra credit to save you. The extra credit I offer in my class is enough to tip the edge. It's not enough to flip the plate, if that makes sense, okay? 6% is the total amount of extra credit I offer. The first 1% is for things like your first day assignments that you're getting today and participating in that class movie night that we do. Not much, but might make a difference. The other 5%, that's way more significant, that comes from your notes. I value note-taking as a skill so highly that I give you extra credit for doing your notes. I don't really nitpick your notes, your format, or anything like that. But you do need to submit your notes. They do need to be legible. I need to be able to read them so I can make sure you're keeping up. If they are digital, that's totally fine. Upload the file. If they're handwritten, take a picture or scan it and upload that. At the end of the term, if you have submitted notes for all 13 lectures, I give you 50 points of credit. There are 1,000 total points in the class. I give you 50 points on top of your lowest exam. That can make a big difference, right? That's how seriously I take notes. And on top of that, I let you use notes during your exams. There's really no reason why you shouldn't be taking strong notes, okay? Please do so. That's how much I value them. Okay, any questions about the grading distribution here? Or about notes or anything like that? Okay. All right. What's the point of the course? Well, there are right answers, right? There's the answer that the institution wants me to give. You know, you're learning how to be a good, responsible person. There is all of that, and I absolutely encourage that. I teach you scientific method and critical thinking using geology as a lens. I love geology, but I don't stop there. We're going to talk about science in my class. I'm going to talk about black holes. I'm going to talk about light. I'm going to talk about gravity. I'm going to talk about other planets. I'm going to talk about life somewhere else in the universe. I go on more tangents in my class than the math class down the hall will. Okay? Like, for real. We're going to talk about some really cool stuff in my class. And I'm really excited to talk about it with you. Okay? But I teach about science, and geology is a subset of that. Absolutely. And most of the time we're going to talk about geology, but I'm so passionate about science, I can't just stop there. Okay? So I'm going to teach you how to think using the scientific method and how to think critically using geology and other sciences here in my classroom. I'm going to teach you hands-on principles for how to apply the things that you learn, how it can make a difference in your actual life. Maybe not day to day, but sometime in your life. Okay? Now I have some standards that we need to uphold here. There will be no cheating whatsoever in my class. What is cheating? There are many different kinds of cheating. It evolves day to day. Obviously, copying someone else's work. Working together on an assignment that is not a group assignment. You can work together on everything in my class except the exams. The exams have to be done separate. I do find students occasionally that have clearly worked on them together. I mean, having the same answer word for word on multiple assignments, come on, right? It's not even inventive, right? And I do nail them for that. What's my policy? Hi there.
Hello.
You're in geology?
Yes.
Nice. We must have had a last-minute registration. Can you go ahead and put your first name on that? Big, bold letters so I can see it from the front of the class, and then lean it up against something. What's your name, by the way?
Adriel.
What is it?
Adriel.
Adriel. Nice. Cool. Real quick, let's take a minute. Where are you from? What's your major? And what are your career goals?
I'm from here.
Okay.
Mechanical engineering.
Mechanical engineering.
And what was it?
What are your career goals?
Oh, at the moment, probably have my own shop.
Okay. Like a body shop or a general mechanic shop or what?
I'm really not sure, to be honest.
Still formulating. Got it.
Yeah.
Got it. No worries. Okay, we're talking about my class standards. No cheating of any kind, copying someone else's work, working together on something that's not a group assignment. Using AI. Now, I'm going to put an asterisk on that. It's almost impossible to not use AI in our world right now. I tried fighting it last year. Couldn't win. Came up with, I have tools that I can use to figure out if students do use AI. And I will use that if you try using AI on an exam. I will penalize you for that. But using AI for something like a lab or a discussion board, at this point, I have turned to thinking of AI as a research tool. It's perfectly appropriate to use research tools for labs and discussion boards, not for exams. The only resource I let you use on exams is your notes. And I do have tools that I can use to figure out if you have used an AI on an exam. Okay? AI will give you answers in a certain cadence, at a certain tone, in a certain format. And there are pattern recognition softwares that will recognize that. So don't even risk it. Okay? Don't even risk it. Now, I encourage you to use AI for research, by all means. Bearing in mind, it's not always right. It's gotten way better over the last few years. 2 years ago, you tried using ChatGPT to do research for you, and it would give you some crazy answers. It would just try to please you. It would make up sources to try and please whatever you're asking. I remember asking it to tell me, to justify to me, why oranges are blue. And it did it. And it made up sources to justify that claim. Because I was insinuating it was true, and the AI assumed it must be. We've come a long way since then, but I've still been able to catch it making mistakes every now and then. So just be careful with that. That's true of any source, though. Wikipedia, be careful of that. Anyone can edit Wikipedia. So you just want to be very careful with the sources you're using, AI or otherwise. Okay? I'm going to insist that we use clean language in my classes. No swearing. Why? Well, you're in college. You have entered into a new path of learning how to express yourself intelligently, and I cannot think of a less intelligent way to express oneself than through swearing. So even though I don't really have anything morally against it, generally speaking, I find it an unintellectual way of expressing yourself, and I'm going to discourage it. So not in my classroom. Outside of my classroom, obviously, I can't control what you do, but please. And that's including the online interactions as well for my online students. And then phones in class. Obviously, my high school students, you are held to a certain rigorous standard there by your high school in the state. So I will expect you to uphold those standards. For my adult students, my non-high school students, use good judgment. Please don't be rude with the way that you use your phones or other devices. If you do need to leave the room and make a call, my adult students, you can go and take care of your business. My high school students, if it's absolutely a call that you have to take and whatever, you have to stay within sight of the window. Okay? Okay. And then I already talked about my email policy. Hello? There we go. I will always answer within 24 hours if it's a weekday, within 48 if it's a weekend or a holiday. Yeah. Any questions about any of this introductory stuff before I jump in to the actual lecture? I'm just going to reiterate this. Please ask questions. This class will be so boring if you're not asking questions. It'll feel like I'm just talking at you. It'll be boring for me. I want you to be involved. I want us to have conversations. I want us to discuss things. And like I said earlier, a science class without questions is meaningless, right? That's the whole point of science, is to ask questions. Try to find answers. There are no dumb questions. I'm serious. Okay, there might be some dumb questions, like asking me about Care Bears or something in the middle of my class. That probably wouldn't be very relevant. But if you have a question about something we're talking about, I guarantee someone else in the class does. Here in the classroom or in my online student body. All right? So you're asking a question for you and someone else. Please don't be too shy to ask questions. All right? Thank you. That being said, shall we begin? Okay. Geology is often treated as a joke. How many times have you guys watched a movie or read a comic or a book, or maybe you've had a friend who liked rocks and everyone just makes fun of them for liking rocks? You guys ever seen The Big Bang Theory? What does Sheldon Cooper think about geology? Yes, that's such a good episode. He drank the night before it. He wakes up, it's the classic wake up, you're just a mess in bed, and he looks over at the other pillow and he starts screaming, "No! No!" And you're like, "Oh my gosh, who's there?" And it pans over and there's a geology textbook. He was reading it while he was drunk. Yeah, he absolutely hates geology. He describes it as the Kardashians of science. He doesn't think it's an actual science. It's hilarious, a little hurtful, but hilarious, right? I mean, there are comic books, and I was made fun of my whole life. How many times have you made fun of me for being a rock guy? A lot, a million times, okay? We just kind of get over it, but geology is really, really cool and necessary. And you're going to learn exactly why it is cool and necessary in my class. You're going to get a taste of that today, but by the end of the 8 weeks, you're going to know for sure. Okay? You're going to know for sure what... Come on now. Don't be doing that. This projector kicks off every now and then. You're going to know for sure exactly why we need geology. Okay? Okay. What is geology, though? The word geology is a combination of two different words that the Greeks threw together. This is what I call Greek word math. They loved doing this. You just throw a bunch of words together and you make a new word out of it, right? Geo, meaning earth, and logos, which means a discourse or a conversation. So geology is literally a conversation about the earth. You're trying to understand the earth. We are discussing it, like we're doing right now. We are doing geology right now, really, when you think about it, okay? Now, there's a whole lot that goes into that, okay? There's a lot of different branches of geology. Just like geology is a branch of science, there are lots of different branches in geology. Things like planetary geology, which is a passion of mine. Talk about that in this class. Definitely you talk about it in 1404. What is planetary geology? Huh? Moon rocks, Earth rocks, any rocks on any planet, anywhere, right? Because guess what? Earth ain't the only planet. It's not even the only planet in our solar system. It's not the only planet in our galaxy by far. Do you know that there's an estimated, I want to say it's 72 pentillion planets in our universe? Exactly. Million, billion, trillion, quadrillion, pentillion. Lots of planets. Not all of them rocky, but a lot of them are. What do I mean by rocky? I mean in our own solar system we have two types of planets. The rocky planets, like Venus, Mercury, Venus, Earth, and Mars. And then the gas giants, Jupiter, Saturn, Neptune, Uranus. Right? So there are planets all over. Most of them, or a lot of them anyway, we don't know enough to say most of them yet, are going to have some component of rock, some hard component to them. That's planetary geology. The rocks we study here are made out of the same elements we find other places. So we're going to find the same rocks in other places too, right? Paleontology. Hey, that's one I already talked about, right? Study of ancient life, the study of history of life on Earth, extinct organisms here on our planet. Even ocean sciences is in here. Why? Because what's at the bottom of the ocean? Rocks. Yeah, there's rocks everywhere. Our planet is made out of them. It's mostly made out of rock. We're going to talk about that. These are all different aspects of geology, okay? So in this class, we're going to learn physical geology. That's the class you all signed up for. 1403, physical geology, studying the Earth, what it's made out of, and how we can understand it. 1404 studies the intersection of that and life on Earth. Okay? All right, so here's your first lesson. Earth is dynamic. Dynamic is a word that means characterized by change or activity. That's the definition. Characterized by change or activity. Someone give me an example. Actually, I would love multiple someones to give me an example of ways in which the Earth is dynamic. What are ways in which the Earth is constantly changing? Weather, fantastic. Yeah, well, it was earlier. I don't think it is anymore, but loved it. Love the rain. Things do change over time. Time does not cause change. Oh my goodness, I am so tempted to go down a rabbit hole about time right now. But I'm going to save it for our conversation about gravity because it's more relevant there. Okay? You almost derailed me. Okay, what else? Technology. Oh, like technology is always changing? Definitely to our civilization. With limited effect on the natural world, but yeah, we'll call that an aspect of it, sure. What else? Tsunamis, sure. Yeah. So natural disasters, right? Those sort of natural disasters cause change, are aspects of that, absolutely. What else? Let's get one more. Can anyone name one more? Climate change, sure. I want some kind of answer from the four in the back here. Any ideas, Leroy? Examples of how Earth changes constantly. No. Seasons, absolutely.
Kind of like oil, like where we use oil, drink oil.
Yeah. So it's carbon cycle. Carbon cycle, absolutely. These are all great examples. Okay, so examples of the way the Earth is constantly changing. We even talked about some of these, right? Disasters like earthquakes. Earthquakes can cause tsunamis, right? That's one of the causes of those. Absolutely. Transgression and regression, which is the rise and fall of sea level. Did you know that that changes over time? We're going to learn about that in this class. Sea level rise, sea level fall. Okay. Volcanoes erupting, growing, exploding, growing again. Okay. All of these are examples. Tectonic plates moving. Do you guys know what tectonic plates are? Yeah? The surface of our planet is broken up into sections that are constantly moving and interacting with each other. Always happening. Now, these are very large, broad, macro-scale events. But that's not the only aspect of how Earth is dynamic. Those aren't the only changes that happen. Changes happen at the microscopic level, too. Things like lithification. Lithification is the process by which loose sediment becomes a rock. How do you go from this to that? You'll learn that. Week 3, we should be learning that. Okay? But it's called lithification. How does that happen? Very small scale stuff over long periods of time. Erosion. Erosion is the transport of sediment. That happens grain by grain, right? So we've got these big macro global scale events and then our tiny little microscopic events, both categories, very important to remember when we're talking about how Earth changes. It's not just what we see happening in the moment, it's the things that are happening under the moment, behind the scenes, behind the curtain. Fossilization, my goodness. Do you know what fossilization is? The replacement of every single cell in an organism with a mineral. How do we have this beautifully preserved Archaeopteryx fossil with even the feathers, some soft tissues remaining behind? Every cell meticulously replaced over probably hundreds of years, okay? If not thousands, okay? These are all aspects of how Earth is dynamic. I like to describe geology as the marriage of physics and chemistry, where biology is that favorite brother-in-law that comes to sleep on the couch every now and then, right? You don't need biology to have geology, but we do have it here, okay? Do we have it in other places? Well, that's the question. That is the question. That's why we are so intent on Mars right now. Do you guys know about the Perseverance rover on Mars? Here's a tangent for you, okay? The Perseverance rover was landed on Mars in 2021? 2022? I think it was 21. Its mission to collect 36 core samples. Basically, it would drill into rock, pull out a sample, bottle it up, and then the goal is to bring those samples back to Earth to study them. Those samples are supposed to return back here by 2035. That was the mission goal. Sounds like a very long time, but when you consider that it takes 6 months for a rocket to get to Mars, then you have to land the rover. Then that rover has to fumble its way across the landscape, collecting samples, bottling those samples up, and then depositing them in one location. And then you have to send another rocket 6 months to get there, and then figure out how to pull those samples back up off the surface, and then 6 months back. 2035 sounds pretty reasonable as a goal. Or it did. Unfortunately, as of about a month and a half ago, our illustrious presidential administration canceled the return flight. The whole point was to figure out if there was life on Mars by bringing samples of Mars rock back here. If there were fossils there, then it would prove that there was life on Mars. We no longer have that plan. It's been canceled. So some other country is going to go get those fossils or those samples probably, and they'll figure it out before we do. Great. Anyways, can geology exist without life? Absolutely. As far as we know, we are the only planet in existence that has biology as a component. But absence of evidence is not evidence of absence. That's something important to remember in science. Okay? Someday we might find out different. As a matter of fact, it's very likely we will find out different. We'll talk about that at a later time, though. Okay? So, let's talk about how the science began. Science in general is the study of existence. Not just Earth, but everything, to study it and understand it. That's the point of science. Geology, that's a study of our planet, right? And then we branch out from there. Biology is a study of life. Chemistry is the study of the interactions between molecules. Okay? Physics is a study of the forces that affect the molecules in existence. Okay? They all work together to make geology and everything else. Aristotle, this fella right here, he was what we call a natural philosopher. Not really a scientist per se. This was before defined science that used methodology and experimentation. This guy was a natural philosopher. He basically spent his time contemplating and philosophizing on everything. Okay? From math to physics to chemistry, geology, biology, as we define them now, but back then, there weren't really those sort of names for them. It was just kind of studying the world, studying life. Okay? Now, he didn't have a lot of the same tools and mental processes that we do now. He would more or less make observations based off of what he saw. So, for example, at one point, someone asked him what a volcano was. And if you're a 300-something BC dude looking at a volcano, ancient Greeks, the pantheon of gods is still all the rage, right? What are you going to look at a volcano and think? It has something to do with a god, right? One god or another. His interpretation was, well, we have a hole in the ground out of which fire is spewing out. This is clearly some tunnel leading to hell or Hades or whatever. Okay? An underworld, which is full of fire and flame and all of that. That was the explanation that made sense at the time. At another point in time, someone brought him a fossilized fish in a rock. Now, what's the interpretation for that? Ignoring everything that we know now. You look at a fish skeleton in rock, and what are you going to think? There must be some types of fish that live in rock. Congratulations, you found a dead one. Try to catch a live one now. Right? That was his explanation. There must be some types of fish that live in rock. We know better now, but he was working with what he had at the time, right? Making conclusions based off of observation alone. Then we progressed over, let's say, centuries, maybe a millennia or two, okay? And we get to this guy named Ussher. Now, not this guy, this Ussher, okay? James Ussher was an Anglican priest in the 1600s. He used a document to try and figure out how old the earth is. He used something called the Bible. Now, I'm going to pause here and just give you all some information, some assurance here. At no point is anything that I teach you supposed to persuade you or dissuade you from any previously held beliefs. There is nothing in all of my years of studying science that can either prove for or against the existence of a God, and I'm not going to try and persuade you or dissuade you otherwise. Okay? In my head, both are perfectly capable of existing. If you want to have any other conversations on that subject, I'm happy to do so outside of class time. But just know that's not my intent here. Okay? All right, so he used the Bible to attempt to figure out how old the earth is. When you go into the Bible, have any of you ever read the Old Testament, by the way? It's got all sorts of genealogy in it. This person begat this person begat this person begat this person. So you can count generations backward. And if you do that, assuming that you know the average lifespan of people at that point in time, you can come up with how old the oldest part of the Bible must be. And that's what he did. He added all of these estimated lifespans together, and he came up with the date of creation being October 22nd, 4004 BC. Which is where the common belief in Christianity that the earth is 6,000 years old comes from. Many Christian denominations on our planet believe that the earth is 6,000 years old because of James Ussher and the math that he did. Now, he's working from one document, one account. Whatever your opinions of that document are, it's still only one source of data. Not great scientifically speaking, but you know who really loved it? The Catholic Church. Now, what's happening in the 1600s around the world? What's the big thing going on right now? What is every major seafaring nation doing? Colonizing. Everybody is colonizing. The French, the Portuguese, the English, the Spanish, the Dutch. Everyone is spreading out and colonizing the world. And you know what they're taking with them? Christianity. And you know what they took with them? This brand spanking new, fantastic, Catholic pushed date of the earth being 6,000 years old, which is why you'll find Christian denominations all over the world now who still believe it. Okay? That's where that comes from. So, this is where that began. Now, the biggest problem with that is, well, if the earth is that young, then why do we have things like mountains and volcanoes and these gigantic valleys and all of that? The answer to that was catastrophism. This is how they explained it away. Catastrophism is the belief that any large feature must be caused by this extraordinarily cataclysmic event. A valley is carved in a matter of days by a giant flood. A mountain is thrust up out of the ground in a few hours by this massive earthquake. Volcanoes form through a single eruption over the course of, maybe a day or two. Massive events must make these massive features that we see. And that worked for a while until people started to think, so where are they? Where are these big cataclysmic events? All this time has gone by and we haven't seen or heard of any of them. We haven't seen a mountain raised in a few days. So what's going on? And that's when people started asking even more questions. Enter James Hutton. I know, a lot of James. It was a very common name. Again, Christianity. Okay? So, James Hutton, in the 1700s, he was a Scotsman. You'd be amazed how many great early geologists came out of Scotland. Until you go to Scotland and then you realize how amazing the geology there is, and then you realize why. Okay? James Hutton started to ask actual questions, and not only asking actual questions, he wanted to find data to back up answers. And so he did. He started collecting data. He would ask a question, and then he would collect information about it. He would collect it, he'd get so much of it until it was practically impossible to say that his conclusion was wrong. This is one of the first attempts of its kind towards that end. Okay? It is thanks to James Hutton and his efforts at collecting evidence that we have something called the principle of uniformitarianism. Now, there are only a few things, 2 or 3 things in my class that I insist you know word for word. That's not the same thing as memorizing it. You don't have to memorize it. Remember, you can keep notes. I need you to know the principle of uniformitarianism word for word. So go ahead and write this down. Okay? Physical, chemical, and biological laws that operate today also operated in the geologic past. Physical, chemical, and biological laws that operate today also operated in the geologic past. What does that mean?
Anything that happens to the earth and our bodies
Yes.
It's always happened.
Yeah, it's always been happening. So then, if that's what it means, what does it imply? I want to hear from someone over here. If the same laws that we see happening today happened in the past, what does it imply? What's the next logical conclusion? Should I give you an example? If I'm watching a river and I see this river deposit 10 tons of sand every day. Actually, let's make it every year, okay? 10 tons of sand every year. And then I go down to the bottom of the river and I calculate there are 100,000 tons of sand at the bottom of this river. What does that mean?
It's consistent.
Assuming it's consistent, how long has that river been dumping sand there?
Forever.
Not forever. In the case of this example, 100,000 years. Okay? Well, 10,000 years because I said 10 tons of sand. But for a long time. The principle of uniformitarianism, assuming that nothing has changed about physics or chemistry, right, which are laws that are pretty consistent, right, suggests that over long periods of time, things continue moving forward at approximately the same pace, barring any external influence. So that river flowing for 10,000 years to deposit that much sand, what does this fly in the face of? What does this give a problem for? Bingo. The principle of uniformitarianism and all of James Hutton's work flew in the face of the doctrine of all the big churches at the time. The earth isn't 6,000 years old, he said. The earth is millions of years old, based on his calculations. People laughed at him. Then they saw all his data. You collect enough data for 20 years and then you share it with everyone? Hard to argue with that. Anyone who was thinking truly scientifically began to realize he must be right. I don't remember exactly what he said. I think he said it was maybe 200 to 210 million years old, which when you've been thinking for generations that the earth is 6,000 years old and then someone says the earth is actually 200 million years old based on all of his data, doesn't that seem like a massive number? We know it's way older than that now. I'll get to that in a minute. But what a mind-blowing idea that something like this, the Grand Canyon, could be formed not by a cataclysm in a day, but by the slow passage of water over millions of years. What an idea. This changed the way that we perceive not just geological sciences, but all sciences. The principle of uniformitarianism is foundational to the way that we perceive the passage of time and the laws of the universe. Okay? So now let's keep talking about time. Geologic time is, when you round it a little bit, about 4.6 billion years old. I'll talk about why it's that old here in a little bit, okay? But we take that long period of time and slice it apart into smaller pieces, easier to eat pieces, okay? Usually resolved in millions of years, okay? So this is the geologic time scale. Going from the Hadean, the bottom of the Hadean, the earliest Earth record, all the way up to where we are now in the Holocene, about 4.6 billion years, okay? With all of this stuff happening in a very small section of it. Life has only existed on Earth for about the last 500 million years. The 4 billion years before that, there was nothing. Okay? Well, as far as we know. Okay? Now, how do we measure time on Earth? There are a couple of ways. Law of superposition. The law of superposition states that anything on the bottom is older than anything on top. Does that make sense right off the what I mentioned there? If not, observe. Here I have 2 layers of rock. Bear with me. They are layers of rock. Okay? Which one was there first? The one on the bottom? Do we agree? Law of superposition. Boom. Drop the mic right there. Okay? That's how it works. Anything on the bottom is older than anything on the top. That's the law of superposition. So we know that anything in the Permian is older than anything in the Triassic right off the bat. Okay? So taking that for granted, let's move on. A is older than B, is older than C, is older than D, is older than E. But what if, I'm not talking about layers of rock, what if I wanted to use things in the rock? Say fossils. Again, knowing that fossils are evidence of life, remnants of life. Can you think of a way that we could use that to determine the general relative age of that layer of rock versus any others? Yeah. What if I have a fossil that's only present in this layer and another fossil that's only present in that layer, and so on and so on and so on? What if I found that fossil 3 is present in this yellow layer here, but if I go 100 miles away, I find fossil 3 present in the purple layer? What does that tell me? Yeah, if fossil 3 is present here in this yellow layer, but then 100 miles away, it is present in the purple layer. Let's say that's sandstone and that's limestone. What?
It exists in both eras.
You're thinking of the right answer in the wrong context. Don't think of these as representing different periods of time, just different layers of rock. Ah, that's the way I want you to start thinking. If the same fossil that was only alive for a very short period of time is present in both this layer here and this layer further away, anywhere where that fossil is the same time. The yellow layer here and the purple layer 100 miles away were deposited at the same time. They must have been because that thing was alive in both. It's kind of breaking your brain a little bit to stop thinking of it linearly. But this is how you need to start thinking. Interpretationally. Okay? Linear is useful, but it's only one way of thinking. Okay? That's called the principle of fossil succession. The order and arrangement of minerals in layers of rock can tell you approximately how old those rocks are relative to each other, not only vertically, like the law of superposition, but across distance as well. All right? I'll tell you about the other way that we measure time here in a little bit. That one's pretty cool. We'll spend some time on that in a minute. First, let's talk about how we do science. The scientific method. Can any of you tell me what that is? Have you ever heard of it before?
Not for a while, I guess.
Not for a while? Give me your best shot.
Scientific method was like the process of developing a hypothesis, testing it, and getting an answer.
Is it 5Q?
The 5 Qs?
I don't know.
Yeah, tell me what those are.
What, when, how, where, and another thing.
Those can definitely be aspects of that. Think of it rather a order of operations, okay? Where those 5 questions are components of probably the first step, okay? Actually, more like the second step. What's our first step?
Create a hypothesis.
Before you can create a hypothesis, something has to happen first.
Observe, then create a hypothesis.
You must observe first. If I don't observe, how do I know what to make a hypothesis about? Hypothesis. Let's see. Emma and Lexi are both wearing glasses. That is an observation, right? Let's make a hypothesis. What is a viable hypothesis for these two wearing glasses? Blind might be a stretch, I don't know. But they might have poor vision. They might need them for a corrective to correct their vision, right? Any other hypothesis?
We prefer them to contacts.
Well, that would still have to do with corrective vision.
Yeah, but
Right.
that's a hypothesis, so if it's
Okay, yeah, that could be one we could go into if we establish that is why you wear glasses in the first place.
Hypothesis just about our vision.
Well, what if you were just wearing them to look hipster? You might wear them to look cool.
Then we're stuck in 2050.
Well, regardless, still a viable hypothesis. So they could be wearing them not because they need them, but because they want to look cool, or they may need them to correct their vision. Those are two valid hypotheses, right? What's the next step in our scientific method? Testing it. How would we go about testing hypothesis? Let's start with, you know what? We could test both of them at the same time. Why don't we? How would we test them? Take off their glasses and make them walk around the room. She took off her glasses.
Yes, I can see just blur.
Honestly, I mean, okay, so I normally save this till the end, but I wear contacts. I have terrible vision. Everything gets blurry that far from my face.
Yeah.
Yeah.
I can see better than you.
Yes, you can. Okay, so we would test this by maybe setting up obstacles in the hallway and telling them to walk down the hallway. Now, after all the HR violations are cleared and everything, and I may or may not have my job for abusing my students, we would figure out.
I'm over 18.
I mean, if I still made you trip over stuff, then I would still get in trouble.
But if I'm okay, I'll do this.
Right. If I had you sign a waiver first, I might be fine. We would figure out for sure that Lexi needs glasses for corrective reasons, and Emma does not.
Okay, well, I can't drive without them on, but I can still see.
Okay, so you do need corrective lenses for some things. It's just the extent to which you need them is different.
I can't live without mine.
Right, so maybe if we did some further testing, if I wasn't just satisfied with one data point of testing, I would then maybe make you drive. I would maybe make you read some letters on that map over there. I would have you do the whole gambit of tests that the optical doctor has you do. And then we would figure out for sure if, yes, you do in fact need corrective lenses. And you know what we would find? We would be able to prove our hypothesis. But now I'm going to ask you to think of this a little different again. Man, I keep getting blown up by emails. We do not, in science, ever seek to prove our hypothesis correct. What? What? Isn't that all scientists do? Don't scientists just want to be right all the time? Well, of course we do, but we need to do it the right way.
Well, don't they also want to disprove other scientists?
Ooh, okay. We never ever want to maliciously disprove other scientists. If we detect that bad science has taken place, it is our responsibility not to expose a bad scientist, but to keep bad science from spreading.
Maybe the theory you're testing disproves other scientists.
Okay, so this is going in the same direction that I'm going. Yes?
Okay, so they want to see if they can prove their hypothesis wrong, because if they can't prove it wrong, that means no one can test them.
Close. So close. Okay. If you start on your hypothesis testing mission and your intent is to prove yourself correct, you're fighting something. Everyone has this innate desire to be right. No matter who you are, no matter how self-controlled you are, how self-aware you are, everyone has this implicit desire to prove themselves right. Do you know what we call that?
Human nature.
I mean, what aspect of human nature? That's what I'm looking for here. There's a word. Bias. Every single one of you has a bias to be right. Have you ever gotten into an argument with someone where you were planning to prove them correct? You have? You've argued with someone? You've knowingly entered into an argument with someone, and in your head you're thinking, I'm going to make sure that they are right out after this.
Yes.
You have.
Whenever one of my girlfriends were like, should I leave him?
Oh, no. That's not what I'm talking about. Okay. I mean...
I didn't say what kind of argument.
like the Earth is round, Earth is flat kind of situation. You know?
Right, you've got people who earnestly, genuinely believe that the Earth is flat. Right? Oh, right. Good call. She needs to take her keys to her husband. Okay. Bias is when we subconsciously or consciously try to prove ourselves correct. The only way around this is through falsification, which is what both of you are touching on here. Falsification is the process of testing where you as the tester have put forth every effort possible to make sure that you prove yourself and therefore your hypothesis wrong. If you are not trying to prove yourself right, you are trying to prove yourself wrong, you circumvent the bias. As long as you're actually doing the job, right? As long as you're not pulling any punches. What's the purpose of this? If I, through falsification, do prove my hypothesis incorrect, what have I found? Let me start with the easier answer. If I fail to prove it incorrect, right? If I cannot prove it wrong, what have I found?
That the original observation is correct.
Right, I have found possible truth. I have failed to disprove it. Everyone else may have failed to disprove it. That's not to say someone in the future couldn't. We disprove past hypothesis all the time. Someone else in the future may disprove me, but for now, we must assume it is potentially true. If I succeed in proving it wrong, what have I found?
Well, you haven't really found the answer. You just found that that answer was incorrect.
Which is true. This is the beauty of truly applying the scientific method through falsification. No matter what, if I am actually applying scientific falsification, I will still find truth. Whereas if I'm only trying to prove myself right, I could be percolating a lie.
Like there's a video that went around recently of flat earthers disproving their own theory.
Yeah,
I love that.
it's great. They actually made a Netflix documentary called Behind the Curve. It's such a great title about flat earthers. It is truly funny.
Well, they did this test where they like took two like things and then they're like,
Yep.
it should just you should be able to.
There shouldn't be any diffraction, but they weren't able to see each other's lights, which means that there must be some curvature, and they thought that they did the experiment wrong, and they like instantly discounted it. It's like, oh yeah, sure, that's why it was wrong. Yeah. Any questions about the scientific method? After your hypothesis fails to be disproven, then we call that a theory. Okay? So any questions about the scientific method? This is one of my favorite comics, by the way. This guy, he goes and pulls the lever, and he gets zapped. And he kind of sits there, he's thinking about it. A normal person would say, I guess I shouldn't do that. What does the scientist do? I wonder if that happens every time. It's so true. It's so true. All right. Can you excuse me just for 1 minute? I need to grab something from my office, and I will be right back, and we will continue the conversation. All right. Earth is divided into spheres, as we call it. I'm not talking about actual physical spheres like balls, okay? We'll talk about the layers of the Earth later. I'm talking about metaphorical spheres, differentiations of space and matter, okay? When you look at this picture was taken in 1979, I want to say. It's called The Blue Marble. Beautiful picture. Absolutely love this picture. What do you see? Describe it. You see yourself?
No, but I'm saying,
Okay.
it's all of us.
I was going to say, that was in 1979. Aren't you still in high school? You see what now? What do you see?
All of us are there, and that's what's it called, finding method.
I mean, we need to assume that humanity is on that. Yeah, is there at the time.
I said a 2D photo.
I'm asking what you see on the Earth.
Storms.
Clouds. Okay. We see clouds. We see atmospheric conditions. Great. What else?
The ocean,
The ocean and land. What's on the land?
Well, you can see like where it's like really green along the coastlines and stuff, and then like where it's
Yeah, we can see plant life. This massive jungle in the middle of the African continent, right?
I think on the other side you would see all the light pollution and stuff.
I mean, light pollution you can't see when you look at Earth. You can only see light pollution when you're looking from Earth out into sky, right? Light pollution is when there's too much light when you're looking at the dark thing, okay? So you can only see it when you're looking from Earth. But yeah, there would be pollution. Sure, we would see maybe some physical pollution. We would definitely see places that have been deforested. You look at the island of Haiti, right? The whole place has been deforested. And then on the other side of the island, the Dominican Republic is still covered in forest. It's like this line where someone just took a brown marker and colored over Haiti, right? Okay, so we've successfully, by looking at this picture, pointed out all of Earth's hypothetical spheres, or philosophical spheres, I guess you would call it. Starting with the hydrosphere. The hydrosphere includes all water on Earth in any form. About 70 to 71% of Earth's surface is covered in water, which coincidentally is about the same proportion of water that's in you. You're about 70% water. Okay? Then we have the atmosphere. The atmosphere is all of the gases that surround the Earth's surface. They make this envelope within which we are capable of living and breathing. The atmosphere is actually a lot thicker than most people would think. Okay? It actually goes about 100 kilometers above the surface. See this little orange strip down here? That's where we live. Most aircraft don't go much above that. Okay? Then we have the geosphere. The geosphere is the solid component of the Earth, from our crust all the way down to the center. These are the different layers we're going to talk about: the core, the mantle, the upper mantle, the crust. Talk a little bit more about those here in a bit. Then there's the biosphere. The biosphere includes all life on Earth, no matter where it is. The birds in the sky, the fish in the sea, you and me on the land, worms in the dirt. Anything alive is in the biosphere. Now, all of these spheres are constantly interacting with each other. As a matter of fact, you and I are kind of aspects of all of them. We are full of water. I am breathing atmosphere. I am alive. I require minerals to survive. I have to consume minerals to survive. There are parts of my body that would not exist without minerals. Do you know your bones and your teeth are made out of minerals? Yeah. We are essentially hung up on a hanger, a hanging network of rocks, for lack of a better term. Okay? Now, all of these spheres interacting with each other create systems. They're constantly moving into and out of each other. These systems are going to have physical effects on the world around us. Like the storm is an aspect of the hydrosphere and atmosphere working together here. Okay? You can even have the geosphere influence this through the introduction of things like volcanoes, spitting super hot gases and ash into the atmosphere that can create storms. Okay? Cycles are repeating processes that occur within the interaction of these systems. Examples of this: the hydrologic cycle, also known as the water cycle. Evaporation, precipitation, runoff, and everything in between takes place within multiple spheres as part of the systems that they interact in. The rock cycle, which we will talk about more in a little bit, takes place within all of these spheres. Okay? The process by which rock is made, melts, changes, breaks apart, gets incorporated into life. All of these take place in the rock cycle. And yeah, they are often dependent on each other. The water cycle is a vital important of the rock cycle. The whole chunk of the rock cycle would not exist without the water cycle. Now, the key ingredient that is universal to all of these systems and cycles is energy. It all requires energy. There are two sources of energy. The sun provides the energy for all of our external processes: weather, climate change, tides, currents in the ocean, erosion, weathering. All of these things require energy. And what is the source of energy here at the surface? The sun. The other source of energy comes from underground. Radiation. Can you guys tell me what radiation is? UV is a type of radiation. Ultraviolet is what that means. But what is radiation itself? I think that was someone slamming into the stairway wall there.
Oh. Hola.
Oh, hi. How you doing?
Good, and you?
Great, thanks.
First thing I called was like
Mercury.
Mercury.
Oh, Marie Curie. Yes. What about Marie Curie?
I want to say she like really discovered it, but I don't think that's right.
She didn't discover radiation. She, a lot of discoveries related to types of radiation and the effect it has on the human body are attributed to Marie Curie.
So she discovered like the effects.
She did a lot of work with the effects of radiation. Yeah. Radiation are particles that have been, for one reason or another, ejected from an atom. Electrons, neutrons, and protons that are blasting out from a central source, the atom that they came from. They have been ejected, pushed out of it at high velocities. And when they interact with tissues, they do damage to those tissues, which is where Marie Curie and other people that studied that come in, for sure. But they contain a lot of energy. And that energy gets soaked up into something. When it interacts with tissues, yeah, it destroys them. When it interacts with rock, it heats it up. We have a lot of radioactive elements inside of our planet. A lot of the densest elements also tend to be the most radioactive, which means that our planet, as it was forming early on, a lot of the denser stuff went towards the middle, where it is still letting off radioactive heat. That heat keeps the inside of our planet super hot. And that heat, eventually, some of it makes its way outward. And when it does, you get things like volcanic eruptions, earthquakes. This is where the energy for the internal processes comes from. Tectonic plate movement. Okay? All right, so now let's talk about that rock cycle. Rocks are made out of minerals. This is a very important concept that we will dive into more on Thursday. Rocks are made out of minerals. A mineral is not a rock. They are not the same thing. Okay? Bear that in mind. I'll dive into that more on Thursday. There are three types of rocks: igneous, metamorphic, and sedimentary. So now I'm going to show you a real quick introduction into the rock cycle, which we will then spend the next several weeks discussing in detail. Okay? So let's start off with, my favorite place to start with the rock cycle is magma. We have magma. Magma is melted rock. Magma and lava, by the way, are the same thing. It's just magma is what we call it when it's underground, and lava is what we call it when it makes its way to the surface. Okay? So we have magma, which then cools and crystallizes. That makes our first type of rock igneous. Igneous rock is only made from the cooling and crystallization of magma and lava. Then we get weathering. Weathering is the breakdown of any type of rock, not just igneous, any type of rock. When it gets weathered, it gets broken down into smaller pieces, which then get transported or eroded somewhere else. Wherever they end up, they are deposited. They are there, they are stuck there. They get piled on top of each other, layer after layer after layer after layer, deposited on top of each other. Eventually what happens is you make sedimentary rock through a process called lithification. There's our second type. Sedimentary rock is only made by the pressurization of sediment. Okay? It's your second type of rock. Then, as our sedimentary rock, or any other type of rock, is buried deeper and deeper underground, it gets heated. It gets heated to the point where it can change chemically, even change physically, but it does not quite melt yet. Can you think of an example of a solid that can change without actually melting if you heat it up enough? Yeah. How about everyone's favorite? Chocolate. I like chocolate. Do you like chocolate? You don't like chocolate? That's okay. We can still be friends. Okay. But you take your Hershey's bar, and when it's in the freezer or the fridge, it's brittle, right? But then you take it and you leave it on your dashboard for a little bit, or just outside in the sun for a little bit, and while it's not melted yet, it's really flexible. That's what's happening here. You're heating up your rock so that it changes physically and chemically perhaps as well, but it doesn't melt. That makes metamorphic rock. It goes through metamorphism and makes metamorphic rock. Now, if I continue to heat up that rock, it is going to pass the melting point, and we are going to get magma again and start the process over. That's your rock cycle. Now, there are exceptions here. There are steps you can skip and steps you cannot. For example, you can just instantly remelt igneous rock and get magma again. That makes sense. That doesn't break any rules. You can have igneous rock that gets metamorphosed without ever having broken apart and becoming sedimentary rock. That makes sense. That doesn't break any rules. You can have sedimentary rock that just gets rebroken down into sediment. You can have metamorphic rock that gets rebroken down into sediment. Those all make sense. They don't break any rules. Things you cannot do. Sediment will never become any kind of rock other than sedimentary rock. Sediment cannot become igneous rock or metamorphic rock. Sediment always becomes sedimentary rock. Camera, stay with me, baby. Okay. Then we have magma will never become any other kind of rock except igneous. Igneous cannot become sedimentary rock without first having gotten broken apart, so on and so forth. There are rules you can't break, but there are steps you can skip. Okay? It's all kind of common sense when you think of it that way. Any questions about the rock cycle? Good. Should we back up a little? We're not going to go too far back. Just about 13.7 billion years. Okay? Let's go back to where this all started. The Big Bang. That's what we call it. Still a theory. Just one that no one has a better explanation for yet. The Big Bang was an explosion, more or less. I say explosion very loosely. A three-dimensional expansion, okay, where before there was nothing as far as we know, an expansion outward of the most basic particle. Do you know what that is? Hydrogen. Hydrogen. Our universe, starting from moment one, and going for a very long time, was only hydrogen. An ever-expanding cloud of hydrogen going further and further apart. Now, right off the bat, really early on, incredibly hot. I'm talking billions of degrees because of all that matter so tightly packed together. But the further all this matter spread apart, the cooler things got. The cooler things got, the more willing they were to come together and make bonds. the closer these hydrogen particles came together, the more mass there was in one spot. What comes along with mass? What is a force that comes with the presence of mass? All things with mass have this. Gravity. Everything with mass has gravity. A hydrogen atom has gravity. And as more hydrogen atoms were pulled closer to each other, the gravity of this overall mass got larger, which pulled more hydrogen together. And so eventually we got these pockets, these clouds of hydrogen that would come together, and they became so massive that they would collapse in on themselves and start a process called fusion. The force of gravity caused them to collapse so close together that all that energy went into doing something called fusion. And this is where the first generation of stars came in. This first generation of stars was fusing hydrogens together and generating a lot of energy as a result, spitting out a ton of radiation. But what was the result? What happens when you combine two hydrogens together? What do we get? Take two hydrogens, you fuse them, spit out the extra particles, you get helium. And this is where our elements came from. Hydrogen to start. But this generation of stars, this first generation of stars, they went from hydrogen to helium. What was made after the helium? Lithium. What was made after the lithium? Beryllium. This is where all of our different atoms came from, all our different elements. Well, not all of them. Every element up to iron was made in this process. The heavier ones after that are made through various other processes, including supernovae. But for now, let's just talk about this. It's called the R process. How the first elements, non-hydrogen elements in our universe were made in the heart of a star. The elements that you are made out of, every single one of them was made in a star somewhere in our universe over the last almost 14 billion years. That first generation of stars, they blew up eventually. They exploded, spreading all of that matter throughout the universe. And then clouds of matter would come together again. And you get your next generation of stars, making even heavier elements. And then kaboom! And then another coalescence of all this matter, making even heavier elements. Kaboom! Until you get where we are now, with all of these different elements, each of which was made in a star, or as a result of the star's explosion. This is what we call the nebular theory, where you have a nebula of gases that comes together and you make a star. That star creates heavier elements. Now, our star, which, do you know the name of our star, by the way?
The sun.
We call it the sun. It's Sol, S-O-L. That's why our region of space is called the solar system. Do you know that? Our star's actual designation is Sol. There are no other solar systems anywhere in the universe because ours is the only system around the planet Sol.
Okay, so wait, question.
Yeah.
Have you ever seen the movie The Martian?
Yes.
Okay, is that why they say, like, they call a day a soul?
Yeah.
It is? Okay.
Because what's a day? A day is one revolution of Earth. On Mars, is it the same? No. As a matter of fact, a revolution of Mars is 26 hours, if I remember correctly. So if you had a 7-Eleven on Mars, it would be closed 2 hours, right? Because their whole thing is they're open 24 hours. No? We don't like that one? Okay. I am prone to bad jokes, just letting you know. Thank you. Okay. I am prone to doing bad jokes every now and then. You have been warned. If I feel like everyone's falling asleep, I will whip a few out. Okay, so, but yes, that's exactly why. All right, so where was I? Right, solar system. Only one solar system. Our star is named Sol. Everywhere else, they are star systems because they are some other system based around a star. Okay, our star, Sol. Okay, so our star was formed. Oh, hold on. I still have the rock cycle lines on there. Okay, so our star was formed, and any matter that did not go into forming our star got stuck in its orbit. Okay, it got stuck in its gravity well. So here we go from this cloud of gases to our star has formed, and what's around our star? This disk of gases and other elements caught in the gravity well of the star. The massive, incredibly powerful gravity of a star. And as time goes on, the heavier elements get pulled closer to the star and start forming planets. The lighter elements, the less massive ones, keep their distance from the star, but they also coalesce and form planets. That's why we have 1, 2, 3, 4 rocky planets close to our star, and 1, 2, 3, 4 gas planets further from our star. Okay, the denser stuff got pulled towards the middle and the lighter stuff stayed further away. So then what about Pluto? Yeah, what about Pluto? Yeah, poor Pluto. I don't know about Pluto. There are so many fascinating theories for what Pluto is. Pluto is no longer considered a planet for a couple of reasons. The first one is it doesn't have a true center of gravity.
So like it doesn't have an axis?
Well, it does. Pluto is like that. Pluto's moon is an asteroid about 1/3 of the mass of Pluto, which means that Pluto doesn't orbit. Its moon doesn't orbit itself. Pluto and its moon orbit each other. The center of gravity for Pluto is actually about here, between the two bodies. Yeah, so Pluto and its moon are actually doing this around each other. That's one of the biggest reasons why we don't consider it a planet anymore. If you were to land on the surface of Pluto, you would immediately get pulled off the surface of Pluto and into space between itself and its moon, because that's where gravity is pulling you. Woof.
So
Right.
it's not a planet because it's dizzy.
It's probably pretty dizzy, huh? So that's one of the reasons. Also, there's a possibility, because of the way that our star system was formed, with the rocky planets towards the center and the gassy ones towards the edge, and because Pluto is way out here on the edge, way further out past our furthest gas giant, there's a possibility, which we won't be able to prove until we go visit Pluto, that it didn't actually come from here. There's a possibility Pluto is a relic of another star system that we captured in the gravity of our star. Who knows how much time ago? Because there's not really a viable explanation for how a spherical planetoid, if you want to call it that, would be out past our gas giants when all of the other rocky matter got pulled in towards the middle. It's possible Pluto existed as an inner planet in another star system, and then something happened to that star system. A lot of things can happen to a star system. Some things that we've observed: sun blows up, everything gets scattered. Sun can just die, dissipate, leaving its planets to freeze and wander through the cold, dreary galaxy. We've seen comets out there the size of our sun. And if one of those does a flyby of a star system, the gravity of that comet, that mass, is going to rip planets away from that star. There's any number of things that could have caused a planet to get pulled away from its original point and end up here. But we won't know exactly whether or not Pluto is ours or adopted from somewhere else until we can go and get a sample and actually do some science on it. Anyways, so Pluto, not a planet, bottom line. Okay, so that's the nebular theory. That is how our star system was made with its current orientation and collection of planets. Now, as Earth is forming during all of this, it starts off really hot and then coalesces into layers with the denser, more radioactive stuff closer to the middle, just like the denser stuff got pulled closer to the center of our solar system. All right, so how old is our planet? Our Earth is about 4.543 billion years old. It's a lot. It's a big number. 4.543 billion. Do you guys understand how big that number is? Well, I have an exercise to do. We think in terms of change. right? Who actually carries change around with them anymore? Not a whole lot of us, right? But you know, you go to the grocery store and a candy bar is still $1.99, right? They still have change on there, so we still have to think about it. So decimals, right? Less than $1. We think in terms of lifetimes, normally in tens, fingers crossed for 100, right? We think in terms of salaries, tens of thousands, fingers crossed for more than that, right? Everyone wants that big six-figure paycheck, right? These days, the US budget is actually in terms of billions, but who bats an eye at $1 billion in the US budget anymore? You put $6 billion in the US budget and we shut down in February, right? It takes so much more than that. You see the article in the news, new $10 billion budget approved by Congress. No one even thinks twice about it anymore. But I want us to think twice about how big that number is. How big is 1 billion? We're going to figure it out. Where is my paper? There it is. How many dots are on this sheet of paper? Throw some numbers out there. Give me something.
300.
300?
$4,000.
4,000?
There's gotta be at least like 100 of every one.
Potentially? Any other numbers? 1,500? No other guesses?
100,000.
100,000? Wow, it's a big jump from 4,000.
Well, I can't discuss, I'm blind.
Yeah, okay, fair. No other guesses? Naomi, how many do you think are on here? 1,000? Huh? More than 1,000. Leroy? 30,000? Oh, just 3,000. Okay. Ilani? 1,500. Adriel, right? What do you think? 5,000. Okay.
You'll hit somewhere.
Oh, what?
So there are enough numbers out
Throw enough numbers out there to hit for somewhere. Well, actually, so you hit it right on the head. There are 4,000 on here. Your first guess was accurate. There are 4,000 dots on this paper. Okay? So how many sheets of paper just like this would we need to reach 1 million dots? I know math, I'm sorry. Divide 1 million by 4,000. What do you get? It's okay to use a calculator. I'm not a math teacher. How many sheets of paper, each of which has 4,000 dots, would you need to reach 1 million dots? Ilani's working the problem. No?
I did it wrong. I did it backwards.
Oh, it's okay. Divide 1 million by 4,000. 250. Okay, 250 sheets to reach 1 million dots. This is a ream of paper, which has 500 sheets in it. Okay, each ream of paper has 500 sheets. So about half a ream of paper to reach 1 million dots. But we're not talking about 1 million, we're talking about 1 billion. So how many sheets of paper to reach 1 billion dots?
The entire ring.
No. How many sheets of paper? If it took 250 sheets to reach 1 million, how many to reach 1 billion? To go from 1 million to 1 billion, you just add 3 zeros. So do the same thing to 250.
A billion is 1,000 million.
Huh? Add 3 zeros.
250,000.
250,000 sheets of paper. 250,000 sheets, each of which has 4,000 dots. If each ream of paper, this is a little more than 2, this is more like 3 inches, but let's assume that generously that's 2 inches, probably 2.5, okay? That's going to make an 83-foot tower of paper. It's about a 7-story building. But we're not talking about 1 billion. How old is Earth? 4.5 billion. To reach 4.5 billion, you would need 2,250 reams, not sheets, each of which has 500 sheets, each of which has 4,000 dots, each of which represents 1 year of Earth history. And that gives you a tower of paper 380 feet tall. Yeah. Perspective. Nice. Let's get one more example. Who wants to go for a walk? We're going to walk around the planet. Okay? We're gonna go get our steps in. Who brought your Fitbits? Are Fitbits even a thing anymore? I don't know. Apple Watches? I don't have an Apple Watch. I have a Galaxy Watch, and it's still blowing me up with emails. Okay, we're going to go for a walk around the equator, assuming that the average human step length is about 2 feet. 1 billion steps is 15 times around the equator. And 4.5 billion is about 70 times around the equator. It's a lot of steps. Are you understanding exactly how long Earth history is? That's a lot. Okay? Huh? It would take a long time, yeah. All right. So now that we understand a little bit more about how old Earth is, let's talk a little bit more about how we differentiate geologic time. I want everyone to pull out a piece of paper. If you don't have a piece of paper, I can give you one. Piece of paper and a pencil or a pen. Okay? And everyone in my online class, please do this exercise as well. Okay. On that piece of paper, you are going to write a long rectangle and divide it into 3 sections. Yeah. Oh, yes, of course. Let's see. You can use this one. Yeah. All right. Rectangle split into 3 sections. All right. In this first section, you are going to write these words exactly. Okay? You're not writing dates or anything. You're writing these words. At the top, started college. Then working down. Started high school, started grade school, learned to ride a bike, learned to walk, and born at the bottom. Don't we read from the top down in English? So then why do I have the first thing at the bottom and the latest thing at the top? Flip it. Do you remember what we called it? When you have the youngest on the top and the oldest on the bottom. This is how we read geologic time and layers of rock. Oh no! You knew it was going to happen. You were waiting for it to happen. There it is, the law of superposition. The law of superposition, oldest on bottom, youngest on top. That's exactly how we're writing this now, okay? So, we ready? Next up, we're going to put the years for this. Now, these are my years. Put your years, okay? Ouch.
1993.
Yeah, 1993.
Like 80 years old.
Close to 80. So close.
You're like 30, 31.
I'm 32. Thank you.
So
So unk. Okay.
I'm not even 20 because I'll be there in like 11 years.
So you're 21.
I'm 20.
You're 20. Got it. Y'all aren't that old. It shouldn't take you that long to remember the dates. All this was forgotten. All right. After you have those dates down, go ahead and write a horizontal line between when you learned to ride a bike and when you started grade school.
Grade school's like kindergarten. Or like,
First grade.
dang, I should have clicked on ride a bike in grade school.
I mean, yeah, if that's how it was for you, then sure. I base this off of my own life, right? So if these two things are flipped for you, then by all means do that. My parents made sure I was a Navy brat. I knew how to swim by the time I was 3. I knew how to ride a bike by the time I was 4.
Yeah, I couldn't ride a bike when I was
10. Got it. All right, so we have the horizontal line. Above that line, write, whoa, I went backwards. Okay, write Schoolian. And below that line, write the pre-Schoolian. All right. What have we done here? We have taken your life, separated by events that occurred, the years associated with those events, and divided it into 2, essentially, geologic time periods based on those events. Everything before you started school and everything after you started school. This is how we separate geologic time. So we have sequential life events, numerical time, and time intervals. Here is a geologic time scale, separated into aeons, eras, periods, epochs, and years, and biological events. So we have our different names, our years associated with those, and the events that caused us to differentiate them from each other. For example, right here, first amphibians. It's pretty important. We draw a line there. First reptiles. Pretty important. We draw a line there. Right? Exactly the same way we did with your own life. So we have our time intervals, the numerical time, and the sequential time, just like we did for your own life just now. Does that make sense? Yeah? You know what doesn't make sense? A penny. It makes 1 cent.
No, it doesn't.
Thank you. And now it doesn't because they don't make them anymore. Yeah. Is the timer for it to not be legal tender, is that expired already? If it does, then they need to stop making things worth 99 cents.
I think they are doing that. They're fixing to start rounding stuff.
All right, good. Finally. Just make it a $2 candy bar. $1.99 never made sense to me. Okay, well, I knew why. It's because for taxing reasons, but... All right. Yeah, we all good with this? No. Sure, yeah, no worries. Any questions while we're waiting? Yeah? All right. So now let's learn a little bit more about the inside of our planet. Let's talk about the different layers of our planet. We have the core, the mantle, and the crust. The core is the center of our planet, and it's broken into 2 pieces, the inner core and the outer core. Did any of you learn in school that under the Earth's crust, it's all liquid rock, it's all magma? Yeah. They still teach that in a lot of schools. We've known that's not true since the 60s. And they still teach it in school. And I don't know why. It's like 50-something years ago we figured this out. Anyways, that's not true. There is only one fully liquid layer of rock in our planet, the outer core. Talk more about that in a few slides. Then we have the mantle, totally solid. That is the layer, the thickest layer of our planet, and it is between the outer core and the crust. And then we have our crust. Our crust is mostly made out of 8 elements. Silicon, aluminum, calcium, sodium, potassium, oxygen, iron, and magnesium. 92% of our Earth's crust are those 8 elements. How do we know, by the way, that the Earth is 4.543 billion years old? Well, the oldest rock we have on our planet's surface is 4.4 billion years old. We found that in Australia. If the oldest rock that we have found on Earth is 4.4 billion years old, how do we know that the Earth is 4.543 billion years old? Any guesses? Great guess, but no. Keep the guesses coming, though. I love it. Is there anything nearby that might give us a clue as to how old the Earth might be if the oldest rock on Earth is not the oldest rock we have from Earth? What? The moon. The moon! The moon used to be a piece of Earth. Early on, in the formation of our star system, as Earth was forming, still mostly melted, it got collided by another planet. Our orbit and another planet's orbit in our star system collided together, making a brand new planet. Our planet, Earth, is a combination of 2 other planets. And all the debris from that collision got stuck in orbit around us and ultimately coalesced into our moon. The oldest rock we have from the moon is 4.543 billion years old, which means that the Earth itself must be at least that old. That's where we get that date. But the oldest rock we have on Earth is 4.4 billion years old. All right, so our crust is thin, relatively speaking. To you and me, does not seem thin. 7 kilometers, 35 kilometers, those are really big numbers, very thick, but compared to the rest of the planet, very thin, paper thin. 7 kilometers is the average thickness of the ocean crust, which is way thinner than the 35 kilometer average thickness of the continental crust. Okay? Continental crust is thicker, but also less dense, which is why it is above the surface of the ocean, while the oceanic crust is below it. Okay? The mantle is the vast majority of the volume of our planet. Okay? About 82%, give or take, of the volume of our planet is mantle. We break it up into 2 sections. The upper mantle, just underneath the crust, and the lower mantle, just above the core. The upper mantle is very solid. I mean, it's all solid, but it's like a mostly rigid solid. It is hot enough that it would be melted, but it can't be because of the pressure it's under. It cannot change from a solid to a liquid because of the amount of pressure it's under being that deep. The lower mantle is way hotter and desperately wants to be melted. But it can't because of the pressure, so instead, it's what I would call squishy. What's a squishy rock like? Think Play-Doh. It's a solid, right? Can we all agree that Play-Doh is a solid? But it's malleable, changeable. You can flex it, you can change it. According to the pressures you put it under, it will change its shape. That's what the lower mantle is like. Okay? The lower mantle is squishy and moves according to the pressures inflicted on it. Then we have the core. You guys ever seen this movie? No? This is one of the movies that we can watch for our silly geology movie night. Adventure story about people going to the center of the planet because something happened and they need to fix it. I won't spoil anything, but very silly. Very fun movie. Anyway, so the core. Earth's outer core is totally liquid. Earth's inner core is totally solid. They are made of the same thing. An iron-nickel alloy. Dense metal. Also, this is where most of the radioactive stuff that keeps the inside of our planet hot comes from. So not only is this really deep, it's also really radioactive, really hot. This liquid iron is about 14 times the density of water, but it still moves like a liquid because it's totally melted. Then the center of our planet, the core itself, is under so much pressure that it cannot physically be anything other than a solid. It has to be. Because what happens when you heat something up, you vibrate it, and as you vibrate it, it separates. That's what melting something does. You're separating bonds from each other because there's too much energy. There is so much pressure here, they physically cannot separate from each other. So even though it is hot enough to be melted, it can't be. That's our solid inner core, nestled inside of the liquid outer core. Now, here's something cool about the core. The inner core is rotating at a different speed and direction than the rest of our planet. Think of if I had a bowl right here filled with water and I put a golf ball in the center. And then I spun the bowl this way. Would the golf ball spin? No. It is independent of the bowl. It is inside a buffer of water. That's what's happening to our inner core. Because our inner core is made out of iron, which is magnetic, and it's inside of a buffer of liquid iron, which is magnetic, and it's rotating at a different speed, different velocity and direction than the rest of our planet, it is generating an electromagnetic field. That electromagnetic field surrounds our planet and protects us from 99% of all of the solar and cosmic radiation that would fry us to a crisp. Do you know why Mars is dead? Well, we don't know if life ever existed on Mars, but Mars looked way different billions of years ago. Mars had water on it. We can see the rivers where they used to be. The Perseverance rover I told you about is drilling for fossils along the edge of a river, an ancient river where one used to be. If there was ever life on Mars, it would have been there. Fish, bacteria, anything else, that's where it would be. We know it was covered in liquid water. There's still ice water at the poles. Mars looked way different billions of years ago. So what happened to it? How did it go from being at least covered in water to where it is now? Barren desert. Mars is smaller than Earth. It cooled off faster. Its inner core and outer core cooled, and its inner core stopped moving. Its inner core stops moving, it no longer makes that electromagnetic field. No electromagnetic field to protect Mars from all the radiation from our sun. The solar radiation slowly blows the Martian atmosphere away, evaporates the water into space, and it's gone. That is what happened to Mars. That is what will happen here. Give it another 2 or 2.5 billion years. Just needs our inner core to stop moving, to cool off enough that we no longer make that magnetic field. That's the ultimate fate of our planet, presumably based off of the example that we see from Mars. Anyways, we're a while away from that. But that electromagnetic field protects us from most of the radiation out in space. Okay. Now, Earth's continents, like I mentioned earlier, are less dense than the oceanic crust. Not by much, just enough. Oceanic crust, about 3.0 grams per centimeter cubed. Continental, about 2.7 grams per centimeter cubed. Barely any difference, but just enough that the oceanic crust sits low on top of the mantle and is covered by water, and the continental crust sits higher in the mantle and is above the water line. Okay? If you want to think of it like this, if you want to think density like this, here we have two boats occupying the same volume. This boat has more mass inside that volume because density is a measure of mass per unit volume. Okay? And so you can see this boat is sitting lower in the water than that boat because there is more mass occupying that same volume of space. Here is a map of Earth's continents. Everywhere you see that is yellow is an active mountain belt. There are two big ones, okay? Your Circum-Pacific Mountain Belt, this one here, comes back around here, and your Eurasian Mountain Belt. That includes the Himalayas and the Alps spreading all the way here into Spain, okay? Those are the two active mountain belts in our world. Younger than about 100 million years. Everywhere you see that is purple is an old mountain belt that is no longer active. Everywhere you see that is pink is a mountain belt that is pretty much weathered all the way down to the surface because it's so old. And everywhere you see that is this beigeish color is an ancient mountain belt that is now covered in sediment. So let me ask you this. Is there anywhere on any continent on our planet that is not associated with one of those four colors? No. So what does that tell you about continents on our planet? They all have to do with what? Yellow being young mountains, purple being mountains that are no longer growing. Huh? No, we're not talking about that one. Pink being dead mountains, you can think of it, and the beige color being dead mountains covered in sediment. All of our continents are made out of what? I mean, yes, rock. Rock from what? What were the words I used to describe all those colors? There was one word I used for all of them. Mountains. Bingo.
You ask a lot of questions that seem harder than they are.
Exactly.
I'm like, this is going to be some complicated answer.
Almost never. I don't expect you guys.
I keep throwing out the simple dumb answers.
Please give me the what seem like simple dumb answers. I will never treat them as simple or dumb. Okay? It's often a more simple answer than you think it should be. Right? I am treating you like students. That's how I aim to treat you. I don't aim to treat you as full-on scientists yet. So I'm not going to ask you a question to which the answer is some complicated thing that you couldn't possibly know, or that I've only said once. Okay? The answer is almost always going to be something simple enough that it's something a student should know. All right? So yeah, mountains. All of our continents are made out of mountains at some point or another. Old, young, long dead, they were all made by mountains.
So wait, an active mountain means it's
Still growing, yeah. Yeah, still pushing it upward, yeah. So everywhere you see that's yellow, that is actively growing.
Which makes sense, California's covered.
Yeah, California is rough.
So all that yellow has a bunch of earthquakes, I'm assuming.
Oh yeah, lots of earthquake activity in the yellow zones. Yep. Great, okay. So now let's talk about oceans. Oceans we separate into a couple of different zones. Okay, you've got your continental margins, which are right next to the ocean. Okay, so we break those off into different areas. Okay, your continental shelf is basically flooded continental rock, because if the ocean levels are high, parts of the continent are going to get flooded, right? Then you have your continental slope with the very gentle, gradual decline into the deeper oceans. Then you have your continental rise, which is where you're deep under the water, and now we are into the ocean crust zone. And it might have some weathered and eroded continental material on top of it. And then we have our deep ocean basins out here, okay? Ocean basins can include everything from very wide expanses. We call those abyssal plains. Pretty boring, just the occasional shipwreck. There can be trenches out there. There can be seamounts. Seamounts are underwater volcanoes. Okay. Seamounts. There's anywhere between 1 and 2 million of those things. It's really hard to keep track, really hard to know where they are. And every now and then, because there's so many of them and it's impossible to track all of them, one of them takes us by surprise. 2 years ago now, a seamount about 5 miles off the coast of Tonga erupted and covered their whole island in ash and sent a tsunami through their capital. Pretty rough for an island whose entire economy is based on tourism, right? Hit them pretty hard. We had no idea this thing was going to erupt. It's impossible to watch all of these. All right, mid-ocean ridges. Mid-ocean ridges are separations between tectonic plates under the water. So where two plates are spreading away from each other, because there are different ways that plates interact with each other, they spread away from each other, they crash into each other, and they rub next to each other. Okay, we'll talk more about that here in a minute. Where two plates are spreading away from each other, that makes a mid-ocean ridge. So this mid-ocean ridge is going to look something like this in cross-section, right? Greatly exaggerated, like we took 1,000 miles and, squished it into just this picture. So here's a continent, here's our abyssal plains. Mid-ocean ridge looks like this. This is the Atlantic ridge as an example, okay? So the two halves are moving away from each other and new oceanic crust material is being made between them, shoving the two plates away from each other, like this, okay? So the Mid-Atlantic ridge is a great example of this. Mid-Atlantic ridge runs through, you guessed it, the middle of the Atlantic, okay? So it's going all the way up here like this, and it's slicing Iceland in half right there. It's literally slicing it in half. This is Thingvellir Park in Iceland. 2017, I was able to go and spend some time in Iceland. This is me diving in that slice where the island has been cut. So for a little bit, I was swimming between two tectonic plates. It was really fun, really cool for geologists. Yeah. Breaking it apart like that. Then when you go further along the valley, there's a place where you can actually touch two halves of the crack at the same time. So I don't know if I was supposed to do that, but I did. Yeah, it was cool. Very fun. Very cool place for a geologist. Iceland is probably my favorite place on this planet, actually. I would live there if I could. I spent a little bit of time trying to convince a mining company to hire me to go and find gold for them in Iceland. And I gave them all the reasons why I was sure there was gold there. And they're like, yeah, we're sure you're right, but we don't have the kind of money to invest in a brand new mine in Iceland. So maybe someday. Okay, let's talk about plate tectonics. Plate tectonics is something that we're going to come back to over and over and over in this class. Okay, so many things are based on plate tectonics. You're going to get sick and tired of hearing me say the words plate tectonics. You might be there already. Okay. Plate tectonic theory basically states that the surface of our planet is broken into a bunch of plates. There are 7 major plates and dozens of smaller ones. We have the North American, South American, Pacific, African, Eurasian, Australian, and Antarctic plates. Okay? And this is a rough general approximation of where they all are right now. Now, they are moving at an average about 5 centimeters a year. That's as fast as your fingernails grow, for reference. Okay, the average person's fingernails grow at about that rate, which does not seem that long. But remember, how old is the Earth? 4.5 billion years. So 5 centimeters doesn't seem like a long time, or it doesn't seem like it's moving very fast. How long or how much distance does that cover in a million years, though?
A little more than 20 billion.
It's 5 million centimeters. Okay. 5 million centimeters. That's a big distance, right? Geologic time, couldn't care less about 1 year scales. We're talking about millions. That's pretty quick, okay? How is this happening, though? These plates don't just move across our surface for no reason. There has to be a driving force. Have you ever heard of convection? Oh, let's talk about convection. Okay, let's say it's winter. Oh, wait, it is. Okay, let's say it's winter and you're on the second story of an apartment building. Your neighbor's hot air is going to do what? The person underneath of you, their hot air is going to do what? Rise. You love being on the second or third story of an apartment building during the winter because your neighbors are paying for part of your heating bill. Their hot air goes to you. It heats up your floor, heats up your air through the vents. Okay? That's great. What happens when I boil water? Steam rises. What happens when same concept, but boil oatmeal? Yes, but you notice what the oatmeal does? It kind of folds itself over. Why is this happening? These are all forces of convection. Convection basically is the principle of heat rises. Hot stuff will rise. Why does this happen? What is it about making something hot that will make it rise through other materials? Have you ever seen a lava lamp in action? I used to have one. The bulb's been dead for like 2 years. I have to replace that thing. I used to have it in here to help with this. Lava lamps. How do they work? You have two different liquids in that jar and a heat bulb at the bottom. What happens when the material falls down to the heat bulb? It doesn't melt, but something does happen to it with that heat. It gets hotter. It doesn't get pushed up. This is the concept of convection. Nothing is pushing it upward. It's heating up because of that light bulb, and as it heats up, it expands. Oh, what's changing? My mass is staying the same. I'm not adding anything. As it is expanding, this is a result of a chemical property. Yeah. My mass stays constant. My volume increases. What did we just talk about that is a measure of mass and volume? There is a property of everything that is a measure of mass and volume. How much mass is in a given volume controls this? Density. There it is. As I am keeping the same amount of mass, but increasing my volume, what changes? Density. What happens to my density? Oh, it decreases. Density decreases as volume increases. Density decreases. It's not compact. You are spreading the mass in more space. So as I am increasing volume by keeping mass, it becomes buoyant. It floats. This is why things float at all. They are less dense than the thing that they are floating in. Styrofoam in water. Golf ball in water. A lot of things in water. But you get the point. Okay? That's why things float. A difference in density. So if I heat things up and they expand, density decreases, buoyancy increases, things float. That's how a lava lamp works. That's how convection at all works. Heat will expand air. That will float in cold air. It will go above cold air. Heat expands water. Heat expands a lot of things, and that's why they float. Okay? So, this is what's happening at in the mantle. Okay? Heat is coming up from the core. As the heat comes up from the core, it interacts with the rock in the mantle. The rock in the mantle is going to move. Because believe it or not, convection affects solids as well. So I'm going to get cycles in my mantle of rock that heats up and does what? And rises. Yes, mantle rock will rise as it gets hotter and therefore less dense. It will rise up and then cool off and fall back down, and rise up and fall back down, and rise up and fall back down. And you get this cycle. You get convection cycles. And those convection cycles in the mantle create drag on the bottom of our continental plates, which causes our continental plates to move across the Earth's surface. So this is where those boundaries come in, okay? So we have the three types of boundaries. We have convergent boundaries. Let me move here. Convergent boundaries, okay? Where two plates are crashing into each other. Why would this happen? What would my convection cells need to be doing? Yes, two convection cells. Yeah, two convection cells in the mantle doing this. Each of them creating drag on the bottom of a separate continent, pushing them towards each other. Oh, is it inevitable? Does it have to? There are two things that can happen in this case. One is subduction, what you're talking about, where one dives under the other plate. The other one is you make a mountain. What controls that? Under what circumstances would one plate dive under another, subduct under the other in a convergent boundary? I mean, gravity is a factor based on, sort of. It doesn't have so much to do with gravity as much as something else we already talked about. What determines whether or not something will rise or fall above another thing? Density again. Which plate's going to subduct, the heavier or the less heavy plate? The denser one's going to subduct under the less dense one. So if I have an ocean plate and a continental plate, which one's going to subduct? Do you remember which one's denser? The ocean plate is denser, so the ocean plate will subduct under the continental plate.
Which is why there's so many like ocean canyons.
Yeah, those trenches next to those boundaries. Bingo. Trenches occur where an ocean plate is subducting under a continental plate. So you get that coastline trench there. Great observation.
I knew that from the Meg.
There you go, the Meg. Man, what a great and terrible movie. It's so good. I love watching that movie.
I love the actor in it.
Jason?
Yeah.
Oh yeah, he's great. It's that movie is actually based off of a book I loved reading as a kid, and I had absolutely no right reading as a kid. There's so much inappropriate stuff in that book, but I loved the concept of the megalodons. I actually have some megalodon teeth here. This is a real megalodon tooth.
I wish I would have known that when my husband was here.
Yeah, I mean, you can always bring them by and show them. I have an even bigger one in the display cases outside my office. All right, what was I saying? Oh, right, we talked about convergent plates. Okay, what about, under what circumstances would I get mountain forming instead?
When they're both continental plates.
When they are equally dense, yeah, continental plates. Can you think of an example where two continental plates have crashed into each other and we're getting a mountain range?
Any of the active mountains, right?
Not necessarily. I want to hear from someone over here. Aiden, I don't think I've heard from you today. It's Aiden, right? Cole. Ah, you prefer Cole, sorry. Cole, can you think of any mountain ranges that have formed as a result of two continents running into each other, perhaps? Can you tell me where in the world it is?
Anyway, because I actually saw a video about this the other day.
Okay.
I'm cool with remembering. It was near Asia, right?
Uh-huh. Yep. I know which ones you're talking about. Do you want to phone a friend?
Yeah.
All right. What do you got?
I got two of them.
Okay.
The Himalayas.
Himalayas. Yep, that's the one you're talking about, right? That's how I thought you were going. Yep.
We should say the Andes as well. In South America, I forgot what they called.
The Andes are made for a totally different reason. Uh-huh. Believe me. We will talk about the Andes next week. The Appalachians are the result of multiple collisions.
We're talking about one singular collision.
Yeah. The Andes, the Andes we'll talk about next week. The Appalachians, we don't really talk about in this class. We talk about ancient mountain building events more in 1404, but we do talk about that in there. The Andes are made from the subduction of an ocean plate under a continental plate. For reasons that I will explain that won't make sense today, but they will. I will explain it in week 2. Okay, but great observation. Himalayas. Well done, both of you. Yes, Himalayas. You guys seen Monsters, Inc.? Welcome to the Himalayas. Snow cone?
Yeah.
You got to watch Monsters, Inc. Okay. It's when they get kicked through the door and there's the snowman. Yeah. Okay. The Himalayas, right there, are the result of the collision of India and Eurasia. India smashed into this continent about 55 million years ago. And the Himalayas formed as a result of that collision. And I'm just realizing my camera is not following me anymore. Hi, you want to stay with me this time? Come on. Come on now. What is your deal today? Yes?
I think it's still over here.
Yeah, it's looking over this way. Hold on a second. Let me figure out what's going on here. Why don't you want to stay with me? There we go. Okay. So now that my camera's actually focused on me, let's go back to what we were talking about. Okay. So the Indian subcontinent right here ran into the Eurasian megacontinent about 55 million years ago. And the camera's still not looking at me. That's fine. Anyone that's watching this online, just look up any map of Eurasia and you'll see the Himalayan mountains, okay? Himalayan mountains right there, currently the largest mountain range in the world, right? Not the tallest mountain though. Tallest mountain is actually Hawaii, if you consider that it starts at the bottom of the ocean and goes up to the top. Do you know what the tallest mountain in our solar system is?
No, Mars or Venus?
It's on Mars.
Mars?
Yes. Olympus Mons. Olympus Mons is a volcano on Mars that's about 3 times taller than Mount Everest. Can you imagine watching that thing erupt? Whew. Fireworks, all right? Okay, so that's convergent plates. Now about divergent plate boundaries, okay? So if the convection cells in the mantle occur because, or if you get convergent plates because you get convection cells in the mantle that are doing this, under what circumstances, what would my convection cells need to be doing to be separating my plates apart?
We're talking about like heat when they're cooling off, right?
Right, so we have heating and cooling going on to make these convection cells.
The cooling part, so that's when they're cooling apart, right?
Yes, so what direction would my cells need to be going? Yeah, the other direction. If they're doing this, going in opposite directions, then they're creating drag on the top, on the crust, pushing the plates apart from each other, which is going to make room for hot rock from the mantle to rise up and make new crust up there. Okay, so that's where we get divergent plate boundaries, where they're spreading apart from each other. Now, what about the third type, transform, where the plates are sliding past each other this way? What do my convection cells need to be doing? So we have convergent, divergent. Ready? You can try this if you want. It's like rubbing your head and patting your belly at the same time. They're going in opposite directions. Okay?
My brain's not processing.
I know, it's hard. But it actually makes the 2 plates go in opposite directions and rub past each other like that. Now, this is the type that's responsible for so many of the earthquakes we see in coastal zones, like California, like we were mentioning earlier. A lot of those earthquakes are the result of this transform boundary, because what's going to happen here is you get friction built up along that edge, and finally it just slips as the friction is overcome by the elastic energy. And that release of energy is an earthquake. Okay? Camera's doing weird stuff. Hello? I think it's time for a new camera, guys. Come on, stay with me now. Why, you don't like me anymore? It doesn't like me anymore. All right.
Your online kids are
Yeah, that's all right. This was the last slide anyway. Okay. Yeah, so next time we're going to talk about matter and minerals. Okay, so today we spent a little bit more looking at the macro view, the broad overview of geology. Starting on Thursday, we're going to start looking at the actual elements, how they work together, how they make bonds, how minerals are formed as a consequence of those bonds, and then rocks from those minerals. Okay, any questions about what we discussed today?
I was gonna ask, like, notes-wise,
Yeah.
if we just, like, do the slides, like, verbatim, like, just take those as notes and then just, like, participate and listen.
Yeah.
Because I find it hard to, like, write the notes and listen.
Yeah.
So if I can just, like, do that ahead of time and just follow along.
Absolutely. I don't nitpick your note-taking strategy. What I care is that it's your work, not mine. So don't take my PowerPoints and submit them as your notes. If you want to, you could literally copy down every word that I say in this class,
As long as it's in my handwriting.
as long as it's you that did it. Because I believe in the 3-part learning method. You hear it, you write it, and you share it. Right? If you hear something, it's in, it's out, you'll forget it before the day is over. You hear something and you write it down, you're that much more likely to remember it, and you have a physical reference for you to look at later. But if it's something that stuck with you, if you heard it, you wrote it, and then you took the time to share it with someone, like our group discussions are meant to help with, it's that much more likely to stay in your long-term memory and help with things like an exam. So I don't nitpick your note-taking strategy as long as you are taking meaningful notes. Okay? I actually had a student that copied down every word I said in every lecture for the entire term. She ended up with a binder of notes that thick. I'm not even exaggerating. Okay?
What I had to do in my biology class.
Right, whatever works for you.
I didn't want to do it.
I'm sure you didn't, but it worked, right?
No, I got
It still didn't work.
I got a C in that class. I blame the instructor.
You blame the instructor? All
100%.
right, all right. Okay, any other questions? All right, let's take a minute now and introduce you to the subject of the labs. All right, because you're going to get your first lab starting on Thursday. Let me show you what the labs look like. So you'll notice that in front of each of you on every table are these kits that have blue lids. Okay, those are your test kits. You are going to get muffin tins like this that have samples in them. I'm going to put this in front of the camera so everyone can see it. Okay, muffin tins that look like this. Okay, each of these has a sample, and you're going to be using the test kits in front of you to find the properties that we are going to learn about in class. Okay, you have the tools necessary, so you can pop those open if you want. Let me tell you a little bit about the tools you have. So you have a piece of glass in there. The glass is for telling the hardness of your mineral, or rock, as the case may be, depending on the lab. Then you have black and white plates of ceramic. Those are for testing the streak. The color that you see on a mineral or rock may not actually be the true color of that mineral. You scratch it on a material like ceramic to see what its actual color would be at the molecular level. You're just leaving a molecule-thick layer on that ceramic. Now, a safety note, please leave the ceramic and the glass flat on the surface of the table when you use them. Don't hold them in your hand, because it's possible they could break, and I really don't want anyone to have any cut hands during a lab. Okay, so just keep them flat on the table and scratch your materials on them then. Okay. Each of you also has a little magnet. You will occasionally find some magnetic materials. You have a magnifying glass. You will have some rocks that have very small grain sizes that you'll need to identify. That's what the grain size charts in there are for as well. Then you each have that little bottle in there. Don't worry, it's not water, it's only acid. Okay? Now, it's very dilute acid. I wouldn't give you the pure stuff. Okay? This is hydrochloric acid. It won't actually hurt you if you get any on you. Your skin will feel a little slick. It's dissolving the outer layer of skin, but don't worry, that's dead anyway. You don't need it. Okay? The top 2 or 3 layers of your skin are dead already. It's just dissolving the top one. Okay? That's why it'll feel a little slick. It won't hurt you. Just go wash your hands. Don't get it on your clothes, though, because it will dissolve the fibers. You'll get holes in your clothes if you get this stuff on you, so be careful. You'll drop a little bit of acid on different samples, and different samples will respond in different ways. Many, or not many, I should say a few in here, will clearly be certain samples, certain minerals, because they will bubble. We call that effervescence. Okay? So that's what the acid is in there for. Let's see, what else? I think that's all the tools you've got in there. The penny is in there as an additional hardness reference. Your glass has a hardness of 5.5. Your penny has a hardness of 2.5. So just an additional way for you to test the hardness of things. Your first 4 labs are going to be identification based. Your first one is about minerals. You'll get that on Thursday. Week 2 is going to be igneous rocks. Week 3, sedimentary rocks. Week 4, metamorphic rocks. Then you're done with identification until the lab exam. Any questions about labs?
How many lab exams do you have?
1 lab exam. Yep. 4 labs that have to do with identification, and then a lab exam about those. And then your final lab, your lab 5, is just about reading maps, and that won't be on the lab exam. Anything else? Clear as mud? Good. Clear as mud or crystal clear? Those are both good references in this class, right? By the way, if you have any questions about the things that you see around the classroom, please feel free to ask. Also, a lot of my really nice stuff moved recently from being in here to being in the display cases out there so that anyone in the community can enjoy them without needing to be in my classroom. So at any point, please feel free to go down there and look at those display cases that I have out in there in the hallway. I think that's all I've got for you today, guys. Look at that. 5 minutes to spare. Okay. If there are no other questions, I'm going to go ahead and end the recording here. If my online students have any questions, feel free to leave those here in the GoReact recording, and I will review those as soon as I have time and get back to you as soon as I can. Until then, see you on Tuesday.